So today in lecture 7, we're talking about force of motion, just a continuation of what we did last time on Monday. Um, to start out talking about force of motion, we got Sir Isaac Newton here in the 1600s and 1700s. That was his life, by the way, right? That's how old he was. How old is he? No, wait, that's how long he lived. There we go. That's how long he lived. But when he was only 25 years old, he formulated most of his discoveries in math and physics, right? So in his book called Mathematical Principles of Natural Philosophy, it's considered the most important publication in physics history. Wow, that's pretty cool, right? Um, I was I I think I was falling out of a two-story building at at the age of 25. So hey, practicing my own gravitational experiment, I guess, because this is a picture of Isaac Newton, and I hear that this actually never happened, but people say that Isaac Newton figured out gravity when he was sitting under a tree tweeting, and and an apple fell on his head, and then he was like, "Oh my God, OMG, tweet tweet, gravity, LOL," right? So, yes, that's an interesting note there, right? So your first question for today is this: Isaac Newton formulated discoveries in what disciplines? Go ahead. I know we're just getting right into it, aren't we? Should be able to scan it a little bit better now. I made it so that it's like smaller but like better aspect ratio. Does that make any sense? Really? Did it work? Did you even scan it for you? I didn't even open up my iPad, so. All right. Let's take a gander and see how you did on this question. I literally just told you the answer, so everybody better have gotten it right. We've got 18 responses. Is that how many people are in here? Lorraine, did you count for me? How many people are in here today? I'm just messing. You don't have to actually count for me. No, just kidding. Okay, so yes, everybody got it right mostly. It's C, both physics and math. The guy invented calculus too, by the way. I'm glad that I don't have to learn any more calculus. I'm sure you guys are glad you don't have to learn calculus, right? It's a terrible time of it. Terrible time. Anyway, so when we're talking about force, right? Force is a vector quantity capable of producing motion or a change in motion, right? So force is capable of changing an object's velocity, thereby producing acceleration. Okay, and I'll show you a picture of what I'm talking about in a second. A given force may not actually produce a change in motion because other forces may serve to balance and cancel the effect, right? So even though you're putting a force on an object, it may not move because there might be another force that's canceling out that original force, right? And so there won't be any movement at all, okay? There won't be any movement at all. So my example here is a tug of war, right? Between, wow, those two kids are pretty strong. There's only three on, wow, there's two on one side and three on the other side. And apparently their forces are equal in magnitude right now, right? We have balanced forces or equal forces. There's no motion because these two kids are somehow, and they're smaller. They look like they're younger in age than these three other kids. And somehow they're holding their own in this tug of war game. So the thing I want you to remember here is that when the balances are equal, right? When the balance, the forces are equal or balanced, F1, which is the first force over here, and F2, which is the second force over here, they're equal to each other numerically as well. Okay? They're equal to each other numerically as well. You know there's not going to be a lot of math because I didn't even open up my iPad, so I can do math for you today. Okay? So let's take a look at another scenario here, right? Now, are these the same kids? Yeah, they are the same kids. Okay, just making sure. Okay, so when we have an unbalanced force, the result is motion, right? Of course. So here, force one is not as strong anymore. Force two is stronger, right? And so now when they're unbalanced, F1 is not equal F2, right? And then the net force is to the right. The kids with three, or the group of kids that have three of them in them, right? So just remember, right, that when the forces are equal, right, F1 equals F2, there's no motion. But then when the forces are unequal or unbalanced, F1 does not equal F2, and your net force goes towards to the stronger force, right? In this case, it's to the right, okay? So your next question is up. In the tug of war between these two dogs, how do you describe it mathematically? How do you describe it? This happens a lot at my house. I have a big German Shepherd, and his name is Yogi, and that's him right there. And I got a little Chiweenie named Kovu, and that's him right there, right? These aren't my dogs. I'm just saying I have dogs that do this, right? And so, although Kovu the Chiweenie thinks he can, fight Yogi the big German Shepherd, he often loses. So, all right, let's see here. Let's see how people are doing. Were you able to scan, Carly? Okay. I was about to blame your high school at first there, but you got it working, so I can't do that anymore. Oh, 22. I like that we have half and half here, right? We have half and half, and we have half and half because A is equal, right, and B is not equal. The picture as shown right now, right, shows no movement at all, right? No, neither dog is falling over. Does that make sense? So right now, little Kovu here is actually holding his own against this big Labrador, this big white lab right here, right? But eventually, he's going to lose, and then the answer will be B, right? But right now, the answer is A. So yeah, I think the reason why this is working for him is because he's like crouching down super low, and then the big dog is super high, and so like if he's really low, he's kind of putting his weight into it as well, right? But eventually he's going to lose. Okay, eventually Kovu's going to lose, and then that's when it becomes B. But right now it's A. Okay, right now it's A. It's good stuff, right? Good stuff. All right, so next thing, let's talk about Newton's first law of motion then, right? Aristotle considered the natural state of most matter to be at rest, meaning, most things in matter, right? They just sit there, they're at rest, right? They're not moving at all. So Aristotle had already figured that out, right? And Aristotle was like back in ancient Greek times, you know? But, and then Galileo also concluded that Galileo, the same guy that did the dropping thing from the Leaning Tower of Pisa, right? He said that objects that are in motion will naturally stay in motion indefinitely, right? So an example of that would be this thing called Newton's cradle right here. When you pull the ball up, it comes down and hits that, and then another one goes, and it just kind of keeps on going for a while, right? So that's pretty cool, right? It's very distracting when you have one on your desk, okay? But it was Newton that finally put it all together in his first law of motion. An object will remain at rest or in uniform motion in a straight line unless acted on by an external force or unbalanced force. Okay? That's Newton's first law. That is Newton's first law. And you can see how Newton came after Galileo and Aristotle. The two of them didn't put it together, but then Newton put it together like centuries later, right? And that happened a lot back in the ancient times. They didn't have the technology we have now, right? And even with the technology we have now, we couldn't come up with some of the stuff that those ancient scientists did, right? So another name for Newton's first law is the law of inertia. Okay, the law of inertia. Okay, another name for the Newton's first law is the law of inertia, and it's the natural tendency of an object to remain at a state of rest or in uniform straight line, right? So a lot of people will say the first law, Newton's first law, is the law of inertia. Okay. Basically, I don't know how many times I have to say this, right? Basically, objects tend to remain in their state of motion and resist change, right? That's kind of like when you're in a when you're driving and you stop real fast, and if you're not wearing your seatbelt, you keep on going still, right? So that's like something that stays in motion even though it's still moving, right? The brake stopped your car, and that's the outside force that stopped the car from moving. But there really wasn't something that stopped you from moving, so you kept on going and hit your head on the the dash, or activated the airbag, right? So what's the thing that you can use as your outside force to keep you from going any further when you put on the brakes? Your hand, or someone's hand, or a seatbelt, right? Your seatbelt. Okay, so Newton even went a step further and he related the object's mass to its inertia. So it turns out that the greater the mass of an object, the greater its inertia. Okay, and then the smaller the mass of an object, the less its inertia, right? Oh, that Newton, he's such a cool guy, I hear. I hear. I bet he would have gotten on to Ghost Hunters. So, here's your next question. Which of the following is true about Newton's first law? It's also known as inertia. The greater the mass of the object, the greater the inertia. The smaller the mass of the object, the less of the inertia. You're such a gentleman, Osvaldo. I don't care what anyone says about you. You're, you're such a good guy. You trying to be the good guy too, Glenn? Okay, so this question is Newton's first law. Wow, everybody's answering so fast. So fast. 22 responses already. The answer to this one was D, all of the above, right? The answer to this one was D, all of the above. All of those are true about Newton's first law. Okay, so congratulations, you all that got them right, right? Good job, good job. So, this is just a little picture, right, that displays or demonstrates what I said last. And you see this big guy here, his cabbie hat, right? This little girl here is having a hell of a time trying to push him in the swing, okay? whereas a little blonde girl here is having a great time swinging because it didn't take that much force to get her to start moving, right? Get her to start moving. The large man has more inertia, more force is necessary to start him swinging, and also to stop him stopping due to his greater inertia. Good stuff, right? Good stuff. Okay, so another example of mass inertia, and you can try this at home, right? Kind of a lame experiment to try, but you can try it at home. If you quickly pull the paper out from a stack of quarters, they stay together because of inertia, right? They stay together because of inertia, right? So Newton's second law is this. Quite literally, it is acceleration is proportional to force divided by mass. Okay, and you don't need to know super any real math about this, right? But the thing I do want you to know here is that acceleration is produced by a force acting on its object, directly proportional to the magnitude of the force, right? So what that means is as the acceleration increases, in the same way the force also increases. They're directly proportional to each other. Everybody got that? That's important to know. Okay, but when you look at acceleration, mass is at the bottom here. It's in the denominator, right? So that's why it's inversely proportional. Acceleration of an object is inversely proportional to the mass of an object. The greater the mass of an object, the smaller the acceleration. Okay. So take away from this slide the thing you need to know to remember, right? Acceleration goes up, force goes up. Okay. Acceleration goes up, force goes down. I'm sorry, mass goes down. Or if mass goes up, acceleration goes down. Okay. Acceleration and force are directly proportional to each other. Acceleration and mass are inversely proportional to each other. Okay? Maybe Cameron was like offended by my story and that's why he left. Okay. So let's take a quick look here about the just a demonstration, not a demonstration, but an example of that last slide, right? Again, we have our equation here. It's not even really an equation. That sign right there means proportional. So as the acceleration goes up, so does the force, or if the force goes up, so does the acceleration. And then on the other side of it, if acceleration goes up, the mass goes down, or if the mass goes up, the acceleration goes down, right? Just remember that if it's at the top of if it's in the numerator, it's direct, and if it's in the denominator, it is inverse, right? So here, if we double the force, we also double the acceleration, right? So here is the normal situation. We got one guy here pulling this cart. Looks like a Home Depot cart, right? And it probably has like a sink on it or something, or maybe a bathtub. I don't know what's on there. Maybe it's a big power tool. I spent a lot of time at Home Depot this summer, building a deck. Couldn't really do anything, you're locked in, and it was just. But then wood started costing a lot of money. So anyway, this guy here is pulling with his force, and his acceleration is there too. But notice when he gets his wife to help, right? When this guy here gets his wife to help, the force doubles because there's two of them now, right? But look what else doubles. So does the acceleration, right? But on the bottom here, for some reason now he wants to pull two of them, two of these carts with like two sinks or two bathtubs, or maybe it's a bunch of wood, who knows, right? But this time though, his force, he's pulling with his force, but then since you're doubling the mass, what happens? Your acceleration is divided by two, right? Does that make sense? So if we have double the mass, then we half the acceleration, okay? One more time. We double the force, we double the acceleration, we double the mass, we half the acceleration, okay? So for your quizzes and for your exam and for your notes, not your notes, your assignment, right? I really want you to be able to articulate the relationships, not even really the numbers, but just know, like if I show you a picture like this, right? Know what's happening and tell me if the force is getting doubled or the acceleration is getting doubled rather, or if the acceleration is getting halved and that kind of thing, right? Just know it conceptually. Okay. There might be a little bit of math, but not that much. All right. Next question. If we double the force, and not the force, but the force, right? Not like the force, like Star Wars, the force, but the force like Newton, the force, right? If we double the force, what happens? Do we have the acceleration? Do we double the acceleration? Do we quadruple the acceleration? Or is it none of the above? Oh, I guess I should see how everybody's answering here. See, aren't you excited? I mean, we haven't done one math problem the entire lecture so far. It's great, right? I mean, I should love math because I'm Asian, but I hate math. So, to the dismay of my parents, I hate math. Oh, dang! I didn't know everybody already responded. That was fast. Okay, the vast majority you've got it correct. Just like I said in the previous slide, when we double the force, we double the acceleration. Okay, or when we double the force, we get two Jedi. Who knows? Okay, or maybe we get two Sith. All right. Well, that reminds me, Star Wars Vision comes out today. I need to watch that. All right. So this is going to be the extent of the math that we do, right? The equation here is the equation for force. And look how easy it is. Force equals what? Mass times acceleration. Okay, that's the equation. Super easy. Okay, super easy. Of course, you already know m is mass, a is acceleration. We've flogged that horse, that dead horse, multiple times. Okay, and then so when we look at the units of it, literally you have mass as in kilograms times acceleration, right? Which is meters per second squared, which we already know, right? So that's the unit. And just to make it shorter, us scientists are lazy, so we call that the Newton, right? When the unit is kilograms times meters per second squared, we call that the Newton. A big N means Newton, naming it after the father of physics, Newton. I actually don't know if that's true. I don't know who the father of physics is, so don't tell me when I said that. So it might not be Newton. I mean, surely it's Newton, right? Who else could it be? I mean, have you heard of anybody else in physics other than Newton? Exactly. So it has to be Newton. Huh? You have somebody else that should be the father of physics? Galileo? Ooh, that's a good one. It's a good one. I'll give you that, Stanley. That's a good one. I mean, yeah. All right. So remember that the Newton is kilograms times meters per second squared, literally because it's mass times acceleration, and that equals the force. Okay. So let's look at this guy right here, right? This is the example we're doing. Okay. We've got acceleration in going this direction because we have more mass over, I'm sorry, more force over here. We have plus 8 newtons over here, and we have minus 5 newtons over here, right? And it's only plus and minus because they're going in different directions, right? But the force 2 has 8 newtons, force 1 has negative 5 newtons. Both of these masses are 1 kilogram, so the stronger force is pulling it net force this way, and so the acceleration is that way, right? The acceleration is to the right, okay? Oh, the other thing to notice too is we always talk about it being a frictionless surface. It's kind of like how we say neglecting air resistance, right? Except here we're talking about frictionless surface. So the question then is, what is the acceleration of the system, right? The question is, what is the acceleration of this system? And so how do we figure that out? We literally just use the equation that we just had, the F equals ma thing, okay? So we're given that mass 1 is 1 kilogram. We're given that mass 2 is 1 kilogram. We're given that force 1 is negative 5 kilogram, sorry, negative 5 newtons. And we're given that force 2 is 8 newtons, right? So again, F equals ma, but you can rearrange it so that acceleration equals F divided by m, right? And then all you have to do is find the difference between the 2 newtons, add up the masses, and that gives you your acceleration, okay? And it's simple that it's doing the difference of the newtons, because if you have 5 on one side and you have 8 on the other side, what's the net amount of newtons? It's 3 newtons, right? So super simple. That's as bad as it's going to get, I promise. That's as bad as it's going to get. Adding the masses together, right? And then finding the difference between the newtons, the forces, and just dividing it, and you get 1.5 meters per second squared. Okay? As your acceleration. So, your next question is this. What is the unit of force? Newtons. Any questions so far while we're waiting for people to answer? So far, we have some pretty simple stuff going on here. Ooh, I'm getting kind of famished. It's getting a little warm. Getting a little warm. Oh, everybody's done it. Good job, everyone. Good job. Okay, so again, the vast majority of you got it correct. The the unit for newtons or force, I should have capital T. This is when you have the force like that with a capital F. That's Star Wars, the force. I'm sorry, that should be a lowercase f. But the unit for the force is kilograms times meters per second squared. So good job, good job. So now we're going to revisit something that we talked about a couple of times ago. I don't remember how long ago. Maybe probably the last exam too, right? And it's this. So mass really is the amount of matter that's present, right? So like how much styrofoam is in this eraser? That's like the mass, right? Whereas the weight is related to gravity. So remember that question on your exam I asked you before? Where would you weigh more, right? On the sun, the moon, or the earth? Well, the thing that's the biggest is the sun. So it has the most gravity. And so you would weigh the most there, right? But your mass doesn't change. Okay? Your mass doesn't change. Same thing goes the other right direction, right? The other direction. If you were on the moon's much smaller than both the sun and the earth. And so the gravity is less. And that would mean you would weigh less. But does your mass change? No. Right? Remember that. Remember that. Okay? So here we have this equation that says W, which is weight, equals the mass times the gravity, right? Which is really the same thing as saying the force equals ma, like Newton's second law. Pretty much the same thing, right? So say I weighed like 100 kilograms. I really wish I did weigh 100 kilograms, but I don't. But say I weighed 100 kilograms. I could multiply my mass of 100 kilograms times the gravity on Earth. Does anybody remember what the gravity on Earth is? 9.8 meters per second squared, exactly. And then that would give you my weight. Does that make sense? That's the difference between weight and mass. Okay, that's the difference between weight and mass. For those of us who want to lose some weight, it's good to go to a smaller planet, right? Okay. So, and that's just a fun fact. The moon's gravity is 1/6 of that of the Earth. Therefore, one's weight changes due to the changing pull of gravity, like between the Earth and the moon. And then in the case of the test question, I asked you the sun as well, right? Okay. So, what is the weight of a 2.45 kilogram mass on Earth and on the moon? Super easy, right? We know that Earth here has 9.8 meters per second squared. All you've got to do is multiply that number by your mass, right? And you get 24 newtons. Okay? And then if you want to do the moon, in the previous question or the previous slide, I just told you that the moon has gravity 1/6 that of the Earth. I probably will never ask you to do this on a test, but just so you know, if I say 1/6, that means you just take the Earth's gravity, right? The Earth's gravity divided by 6, because it's 1/6, times the mass, 2.45 kilograms, and you get 4 newtons. You get 4 newtons. So look how much less you weigh on the moon, right? Look how much less you weigh on the moon. It's awesome. Awesome stuff. Okay? It's not too much math, right? Is it okay so far? We're doing some simple stuff, right? Just multiplying and dividing, right? Not even solving for x, right? Shouldn't be that. I don't want to overwhelm you with like mathematical formulas and equations. So this is probably the extent of it. Okay, so now let's talk about mass and acceleration. Oh, we're doing good on time. It's perfect, perfect, perfect. Acceleration is due to gravity. What? Sorry. Acceleration due to gravity is independent of mass, right? But you knew this already because Galileo, Stanley's favorite scientist, right? His father of physics, he did that experiment where he was at the top of the Leaning Tower of Pisa, right? and he dropped a rock that was small and a rock that was big, and they both accelerated to the ground at the same rate, right? Regardless of what the mass was, right? So the acceleration due to gravity is independent of mass, okay? And the reason why that is because here we have, just one physics book. I guess this is our textbook right here, right? Intro to Physical Science. And it's fallen, right? But then you put two of them together, right? And then that means you have twice the force and twice the mass. The twos cancel out, right? And you still get G again. And that's why acceleration due to gravity is what? Independent, right? Of mass, okay? Because two forces divided by two masses is the same thing as one force divided by one mass, right? It's crazy stuff, crazy stuff. So just remember that statement right there. Acceleration due to gravity is independent of mass. Remember that right there. Okay. And this is your next question. Just for you, Carly, I could put a monitor like right in front of your face, so you could scan it. You got it this time.
No, it works like every other one or every.
I'm just giving you a hard time because you're from Martin High. Acceleration due to gravity is dependent on mass, independent of mass, independent velocity, or none of the above. At some point, just so you know, when I'm giving you the answer to the question, like right before the question, I would like everybody to get it all right. Okay? Everybody should get the answer correct. Wow, everybody's already responded? Look at that! I said that and everybody got it all right. I'm so happy. I'm so happy. Good job, everyone. Good job. Okay. The last thing we're talking about today is friction. Not friction in the personal, interpersonal sense with another person, but friction in the science sense, right? Friction is a resistance to relative motion that occurs whenever two materials are in contact with each other, right? They're found in all states of matter. Solids can have friction with each other. Liquids can have friction with each other. Gases can have friction with each other, and so can people. People can have friction with each other too. In some cases, we want to increase the friction, like sand on ice. I don't understand what that means. Like sand on ice. In other cases, we want to reduce friction. Oh, I see. Like whenever the ice is over, right? We put sand down so that the ice doesn't make your cars slide all over the place. I thought they put salt down. I didn't know they put sand down. Is it salt or sand? Okay, so what is salt? Wasn't it salt?
I think they put more sand down for like oil spills.
Really? Huh. Interesting. Well, whatever it is, sand or salt, we added on there to add more friction so we're not slipping and sliding like we did back in the deep freeze of February. What I call Snowpocalypse 2021. Or maybe it should be called Ice Apocalypse 2021. which is there was already a Snowpocalypse 2014 too, so I got to be careful there. That was when people were down in Galveston were building snowmen. I mean, that's a problem when you're building snowmen in Galveston. That's just something going on there. Something wrong. Something wrong there. Okay. So and then sometimes we want to reduce friction, and that's motor oil, right? When you change your oil in your car. Okay. So there's two types of frictions. There's static friction. This occurs when the friction force is sufficient to prevent the relative motion between the surfaces, right? So when two surfaces are against each other and they don't move, that's static friction. And then there's kinetic friction, also known as sliding friction. It occurs when there is a relative motion between the two surfaces in contact. Okay? So that's like sandpaper on wood. right? Makes sense? Kinetic friction is generally less than static friction. Well, that makes sense because in kinetic friction, you're moving around, so there's not enough friction to keep it from moving, right? So static friction is going to be more when you can't move anything at all when you got static friction going on. It usually takes less force to keep something moving than it does to start it moving. So that's actually interesting because, like, have you ever heard of the thing where they say when you start the car, when you start the engine of your car, you actually waste more fuel than if you just kept it like idle for a while? So it's the same thing, right? If you were to just leave your car idle for like 15 minutes or something like that, because say you were running into your house. Why would you leave your house for 15 minutes? I don't know. Anyway, say you need to go back in your house after you started your car. Would it be better to stop the engine and go in your house, or just leave it running? It'd be better to leave it running because if you turned off the engine, right? If you're in a trustworthy neighborhood, if you turn off the engine, right, and you have to start it up again, you actually expend more gas when you have to start it up twice. Okay, but if you just let it run idle while you're going in there to get your key, well, I guess you wouldn't get your keys. So how did you start your car? Get your phone, right? If you had to go back in there to get your phone, I would just leave your car running because then you expend less gas. You expend less gas. And this is the same kind of thing here, right? It usually takes less force to keep something moving, like the engine parts of your car, right, than it does to get it started moving, like the engine parts of your car, right? Okay. That's why it's so hard to start a lawnmower. Ever try to start a lawnmower? Holy mother, that's tough, right? Because those engine parts have been sitting there for a while. And, if you're anything like me, I only mow my lawn like once every 2 months, and so it's really hard to start my lawnmower. Maybe I should just get an electric one. I hear those are awesome. All right, next question. What is true of static friction? It occurs when there is a relative motion between. It occurs when the friction of the force is sufficient to prevent relative motion between. Or the kinetic friction is generally more than the static friction, or none of the above. This one's a little tricky. It is contagious. Hi, Dean Rodriguez. How are you today? So, has everybody answered? Let me see if everybody's answered. Let's see what's happening here. Forms. Friction. There we are. This one's a little tricky. But yes, again, the vast majority, you got that one correct. Good job. I'm very proud. Right? So which is true of static friction? I lost my laser. Where did it go? There it goes. Right? It occurs when the friction force is sufficient to prevent relative motion between surfaces, right? So that was the definition from for static friction. And then this was the definition for kinetic friction, right? So it couldn't be that one. And then I already said also in the previous slide, right? It's actually static friction that is more than what? The kinetic friction, not the other way around. And that's what that is, the other way around. And so since that B is true there, none of the above is not the correct answer either. Okay? So friction is described in this thing called the coefficient of friction, okay? And I'm not going to make you do any super hard math with this, but I just want you to understand the concept behind the coefficient of static friction. The coefficient of friction, right? So it's represented by mu, the Greek letter of mu, and it's dimensionless quantities used to characterize a particular contact situations, right? Both coefficients of static friction and coefficient of kinetic frictions are determined experimentally for a wide range of contact surfaces, right? And then this right here just demonstrates what I said before, where the static friction, right, is more than the kinetic friction, right? So what that means, and what that shows here then, is that the coefficient of static friction is also greater than the uh, coefficient of kinetic friction, right? Does that make sense? So this literally, talking about the talking about the coefficient of friction here describes what my previous statements were before the question, okay? And then our last slide for today is just a comparison of different static, coefficient of frictions, okay? Kinetic and static. So see, if you look here, right, we have aluminum on aluminum, so two pieces of aluminum together, right? The static coefficient of friction is 1.9, right? And then the kinetic is 1.4, right? Aluminum on steel, a little bit less friction going on there, 0.6 and 0.61 and 0.47, right? But I think the most interesting thing is here, right? We have Teflon, which is the stuff that we have on our frying pans. So we have non-stick frying pans and stuff like that. That's how my steak and my eggs don't get stuck on my frying pans when I'm cooking. Sometimes they still get stuck though. Maybe I'm just not cooking them hot enough. Maybe it just needs to cook a little bit better on the underside of my sunny side eggs, right? But Teflon on steel, right? Look how much static friction goes down. The coefficient goes down. It goes all the way down to 0.04, right? Add a little bit of oil to that too, a little bit of Pam, might be even zero, and your eggs will come straight out of the frying pan, right? Your steak will come straight out of the frying pan. Well, steaks don't ever get stuck in the frying pan, but eggs that do get stuck, or cheese, right? Okay, so rubber on concrete, right? So this is like tires driving on the road, right? Rubber tires driving on the road. And when it's dry, the coefficient of static friction right here is 1.2. You know, the movement for the kinetic one is 0.85. But then when it's wet, it goes all the way down to 0.8, right? And 0.6, right? And the interesting thing about that is that the roads are actually the most slickest when there's not a ton of water on the road, but it's like a film of water on the road, right? And that's really what reduces the coefficient of friction so much that you can do things like hydroplane and glide. Uh, yeah, hydroplane. That's right. Yeah, hydroplane. In fact, I don't know if do do any of you have this problem? Not a problem, but when you're driving on wet roads and you tend to like hydroplane just a little bit, your car starts beeping. You know, on my car, I have this little thing it's a little indicator light that shows up. And if I'm even slightly hydroplaning, right, the computer can detect it, right, that I'm starting to slip, right? And it'll start blinking this little light that looks like a car in like a swiggly road, right? Does anybody know what I'm talking about? They have it on Toyotas. I don't know. I'm a Toyota family, so I don't know if anybody else has it on their cars, right? Well, that's an indication for you not to like brake real hard, right? To just slow down, but not brake so hard because then you'll hydroplane somewhere, right? So a computer can actually detect friction. Isn't that crazy in your car? It's pretty crazy, right? And then we got wood on wood here, right? 0.58, 0.40, and then lubricated ball bearings uh, less than 0.01, right, for both. And ball bearings are in like um, the thing I can think of right now that's probably that everybody knows is like the wheels in chairs, right? Like when you spin around in your chair, those are on bearings, right? And they spin real easily, right? If you take it apart literally inside, they're like little balls, little steel balls, and it makes it so you can swivel your chair around, right? And fun fact, Thomas Jefferson invented that, by the way. If you did, he's not my favorite president, right? He's not my favorite president, but he did invent the swiveling chair, right? I saw, I read something about that when they were writing the Constitution or something like that. So, anyway, that actually ends today's lecture.